Hello students, welcome to lecture 6 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on basic electromagnetic theory, and here is the lecture outline. So we'll give you a very brief overview of electromagnetic optics, take you through the divergence, curl and gradient operations, briefly discuss about Gauss theorem and Stokes theorem, the constitutive relations, and finally we will give you an overview of Maxwell's equations. So electromagnetic optics is basically a vector theory comprising an electric field and a magnetic field that varies both in time and space. So here is right way to present it, that you have electromagnetic optics and then you have wave optics, which is an approximation to electromagnetic optics that relies on wave function, which is basically a scalar function of time and space. And then you have ray optics, which is again a limit of wave optics when the wavelength is very short. That means the objects are much larger than the wavelength involved. So in short, you can say that electromagnetic optics encompasses wave optics, which in turn reduces to ray optics in the limit of short wavelengths, right. So from this particular figure we can understand that wave optics has a far greater reach than ray optics. Remarkably, both approaches provide similar results for many simple optical phenomena involving paraxial waves, such as the focusing of light by a lens and the behavior of light in a graded index media and periodic systems. But wave optics can offer something ray optics cannot, and that is basically the ability to explain phenomena such as interference and diffraction. However, wave optics is unable to quantitatively account for some simple observations in optical experiments as well, such as the division of light at a beam splitter, and that is when some fraction of light is basically reflected and transmitted. It turns out to be depending on the polarization of the incident light, which means light must be treated in the context of a vector in that case, not as a scalar, okay. And this is where the electromagnetic optics enter the picture, okay. So in common with radio waves and X-rays, light is an electromagnetic phenomena that is described by a vector wave theory. So electromagnetic radiation propagates in the form of two mutually coupled vector waves, that is an electric field vector or wave and a magnetic field wave. So in this particular course we are going to focus on radiation type, microwave and visible. We have already seen this. Frequency will be like 300 megahertz to 300 gigahertz, wavelength ranging from 1 mm to 1 meter, that is for microwave. For visible we will be talking about 430 terahertz to 790 terahertz, and that implies vacuum wavelength of 380 nanometer to 700 nanometer. Now if you quickly have a look at the electromagnetic spectrum from low frequencies to high frequencies, okay, and so the wavelength basically moves the other way, so short wavelength to long wavelength. You can see radio waves, then you have microwaves, infrared radiation, visible light, and then you have UV, X-ray and gamma rays. So this way the frequency keeps on increasing and the wavelength keeps on reducing, right. So you can wonder this range, how vast it is. The wavelength starts from 10 to the power 3 meter, that is like kilometer, okay, to 10 to the power minus 12 meter, that is a picometer. So the variation, wavelength variation over this range is of 10 to the power 15 meter. It's huge. Now before proceeding to Maxwell's equation for electromagnetism, which is basically guiding the relationship between the electric and the magnetic field, okay, and also the materials involved, we can go through some of the important operators which are used in vector calculus and these operators are going to be very useful for calculation of electromagnetic phenomena. So, there are three main operators in the vector calculus, okay, that quantify changes in the field. The first one is called gradient, that change in magnitude of scalar field. So, here you can see that this basically shows you the gradient. Okay. So, here you have some positive charges, here is some negative, more positive charges. So, this is the way it shows the change in magnitude in this direction. Here also, here is more negative, here is less negative. So, this is the gradient. Okay. So, if you take the gradient of a scalar field, you are basically going to get a vector. Next is divergence. It tells you about the source of vector field, right. So, here you can see that the divergence of a vector field is basically a scalar. So, if you have a positive charge, you have field diverging outward. If you have a negative charge, you will be having field that is coming towards you, okay, converging fields. So, curl basically tells you about the rotation of a vector field. So, here you can see that this is one particular way of rotation of the electric field vector, this is another rotation. Okay. So, these are the two different orientation. So, this tells you the arrow coming out of the plane, this tells you about the arrow that goes inside the plane. Okay. So, the basic operations basically allow extracting information about the distribution of electromagnetic fields, energy associated with the fields, electromagnetic radiation, and so on. So, the four Maxwell's equations are typically going to be written in this vector calculus form. So, if we think of the differential form of Maxwell's equation, we will see that the equations are basically written in the form of vector differential operator, which is also called as nabla operator. Okay. So, in a 3D space, vectors can be split into orthogonal components and the partial derivatives can be calculated accordingly for each directional component. So, the nabla or the del operator is a vector differential operator which can be written as this. So, I cap dot ox plus j cap dot oy plus k cap dot oz, right. Nabla can be used in Laplacian operator also, where it is referred as nabla squared or del squared, that denotes basically double differentiation. So, del dot del, or you can just write it as nabla square or del square, is nothing but dou square dou x square plus dou square dou y square plus dou square dou z square or dou z square. Okay. Now, coming to the gradient of a scalar is a vector, right. So, how it works? A scalar's field gradient becomes a vector field whose magnitude basically tells you about the rate of change and the direction tells you in which way the change is increasing, right. So, it tells you that in general direction, or you can say it points in the general direction of the scalar field's greatest rate of increase. Okay. So, if this del is made to operate on a scalar field f, so f you consider as a scalar function here, then the following notation can be used. So, you can simply write grad of f, or you can just write del f. So, what will be del f? Del f is nothing but del is given by this, okay, I cap dot ox plus j cap dot oy plus k cap dot oz times f, or you can simply write it like this, I cap df dx or dou f dou x plus j cap dou f dou y plus k cap dou f dou z. So, that way you can find out the gradient. Now, next important operator is divergence of a vector. So, the divergence basically quantifies the magnitude only, okay. It does not tell you about the direction of the amount of vector field which basically flows out or into a particular region. So, in other words, you can say that the divergence basically calculates the amount of source or sink for a given field. So, divergence of a vector field will be a scalar. So, if del is made to operate on a vector function f, so you take f as any vector field, okay, then the following notation can be used and you can see the divergence turns out to be a scalar quantity. Okay. So, divergence f, or you can simply write div f, or you write del dot f. So, that is also divergence. So, the full notation will be this field has got its x, y and z component. Del operator also has got its partial, you can take the partial derivative along each component, and once you do that you get this one, dou fx dou x plus dou fy dou y plus dou fz dou z. So, this is what is your divergence. So, as I already mentioned that when there is a source you have the field flowing out, if there is a sink there will be a field flowing into. Next important parameter is curl of a vector. So, the calculation of curl basically quantifies the amount and direction of rotation of a vector field, which is the result. Okay. Here the result is also a vector which is perpendicular to the field of rotation. So, in a sense, when a pseudo vector is used to represent rotation in physics. So, you can see that if you have a rotation around the right hand rule, the thumb basically tells you that the vector direction is outward, right. So, it is basically telling you the direction, okay, and the vector is perpendicular to this plane of rotation. So, this screen is basically the plane of rotation and the vector is basically coming out of the plane. On the other rotation, if it is going say clockwise in this direction, okay, so you will see it is doing like this. So, in that case, okay, from the plane of polarization the vector is basically pointing inward. So, in a 3D Cartesian system, the curl of a vector field can be calculated from its orthogonal component. So, curl of f can be written as del cross f, okay, that will be simply del is a vector, f is a vector. So, you just do the cross product. So, it will be I cap dou fz dou y minus dou fy dou z plus j cap dou fx dou z minus dou fz dou x plus k cap dou fy dou x minus dou fx dou y. So, that way you can calculate the curl of a vector field, which is also a vector. So, with the basic understanding of the three main operators in vector calculus, we can move on to have a quick recap about the Gauss theorem or the divergence theorem. These are important in calculating different fields. So, we are having a very quick overview of this. The theorem states that the flux of a vector quantity outward through a closed surface S, so this is the closed surface S, is equal to the integral of the divergence of the function in the enclosed volume V. So, whatever the volume this closed surface is enclosing, okay. So, if you take the divergence of this vector field over that volume, that will be same as the outward flux that is going out from this closed surface S. So, how this V and S are basically related? So, this closed surface is basically enclosing a volume V. So, you can say if the given volume does not contain a source or a sink of the vector field, then the next then the net flux through that volume must be 0, right. So, if it contains a positive charge, then there will be like electric flux lines coming out of it, okay, or even if it contains a negative charge, there will be something. But if there is no net charge, then there will be no net flux through this particular volume. Okay, that means all the flux entering the volume must also leave that volume. So, it is possible to find such volume that will entrap an electric charge, because each electric charge represents an electric monopole, and that leads to the Maxwell's first equation. And if you try to reapply this to magnetic field, you will see that it is not possible to find any volume that can entrap a magnetic charge, so that the magnetic field is divergenceless, and hence you can say that there are no magnetic monopoles, and this basically leads to the Maxwell's second equation, right. Now, let us look into the other theorem, which is also very important, the Stokes theorem, that states that the surface integral of the curl of a vector field f over any open surface S. Okay. So, if you want to take the surface integral of a vector field over any open surface S, that is going to be equal to the closed line integral of the vector along the contour enclosing the open surface, right. So, it means if you want to calculate all these small curls over this entire surface, why not you just calculate the curl, or you just calculate the integral of the vector along the contour that encloses this particular open surface. Okay. So, you can write that the curl of f dot dA, you take the integration over this entire surface, that will be same as the contour line integral or closed line integral of the vector over this particular contour. So, it basically relates the surface integral of the curl of a vector to the line integral of the vector itself, right. That is simply you can say. So, in other words, the circulation of a vector around a given boundary is equal to the net curl over the whole surface of the patch limited by that boundary. So, in this particular equation, you can see S is basically denoting the analyzed surface, F is basically the analyzed vector field, A is the vector normal to the surface, C tells you the closed curve as you can see here, okay, and L is basically the tangential to the curve C. You can make L like this. Okay. So, this is a easy way to remember how Stokes theorem works. Next comes constitutive relationship. So, that is important where the light matter interaction is taken into consideration. So, in order to apply Maxwell's macroscopic equations, it is necessary to specify the relations between displacement field D and electric field E, as well as the magnetizing field H with the magnetic field B. Okay. So, equivalently we have to specify the dependence of polarization P, which is coming from the bound charges, and also magnetization M, which is basically the bound current, right, on the applied electric and magnetic fields. So, the equations specifying this response of the material is called the constitutive relationship. So, dielectric permittivity is basically diagnosed. Dielectric permittivity is a diagnostic physical property which characterizes the degree of electrical polarization a material can experience under the influence of an external electric field. So, how do you measure it or how do you define it? Dielectric permittivity can be defined as a ratio between the electric field within a material and the corresponding electric displacement D. Okay. So, here you can see the equation D equals epsilon naught E, right. So, this is an unpolarized material. So, the polarization is 0, electric field is also 0 when it is not there. So, displacement is also 0. But as soon as, so what is happening to this material when exposed to an electric field? you will see that the bound electrical charges of opposite sign, they try to separate from one another, right. For example, the electron cloud of the atoms will try to move away in the direction of the electric field, or you can say that the electron clouds of the atoms will shift its position relative to their nuclei. So, in that case there will be scarcity of negative charges. So, the positive charges are left behind. So, you can think of those as positive ions, and then you have the electron cloud shifted. So, those are the negative charges. So, these are basically the bound charges that leads to polarized atomic elements. So, the extent of the separation of the electrical charges, so how far they will separate within a material, is basically represented by the electric polarization P. Now, the electric field, electric displacement and electric polarization, these are the three terms. They are related by this particular equation, which is called D equals epsilon naught E plus P. Okay. So, epsilon naught is vacuum permittivity. Okay. So, this is how you write it as epsilon, D equals epsilon E. So, this epsilon is basically taking care of both the vacuum and the polarization aspect of the material. Similarly, when you expose any material to any applied magnetic field, the collection of the individual magnetic dipole moments within most materials will attempt to reorient themselves along the direction of the field. So, this will basically generate an induced magnetization in the material, which will contribute towards the net magnetic flux density inside the material. So, you can say you will have B, the magnetic flux. Okay. So, this generates an induced magnetization which contributes towards the net magnetic flux density inside the material. So, B equals mu naught H plus mu naught M. So, that altogether can be written as B equals mu H. So, mu naught is basically the permeability of the free space, okay, that is 4 pi into 10 to the power minus 7 Henry per meter. So, you can write B equals mu naught mu H, B equals mu H. So, the degree in which the induced magnetization impacts the magnetic flux density basically depends on the material's magnetic permeability. So, magnetic permeability is mu, that is defined as a ratio between the magnetic flux density B within the material and the intensity of the applied magnetic field H, provided that both the fields are very weak, right. So, B equals mu H. So, you can understand that mu will be nothing but B by H. Okay. So, for now we can only focus on material which are not magnetic. So, the magnetization is 0. In that case, you can simply write B equals mu naught H. Now, with that we understand the fundamentals that is required for Maxwell's equation, and then let us go and describe this golden 4 equations that are vital in understanding the behavior of any electromagnetic wave. So, we have seen that electromagnetic field is basically described by two related vector fields that are position of both that are function of both position and time. So, you can write electric field as ERT, magnetic field as HRT. So, Maxwell's equation has not just come up like that. After the myriad of researches carried out for fundamental reasons behind the source of electromagnetic field and the relationship between the electric and the magnetic field by pioneering scientists like Ampere, Coulomb, Faraday and Gauss, Maxwell was the one who combined those 4 equations to describe the electromagnetic field behaviors. Okay. So, he proposed a set of fundamental equations in 1865, okay, and that is him. So, he basically advanced the theory that light is an electromagnetic wave phenomena, and he formulated those fundamental set of equations, and that is why those 4 equations bear his name. Okay. Though actually those 4 equations are basically all done by other scientists, like the first equation, which is basically telling you the divergence of electric field equals rho v by epsilon, is Gauss law or Gauss law of electricity of and then del dot H equals 0, that is basically Gauss law for magnetism. Okay. The next two are the curl equation, curl of E and curl of H. These are also basically Faraday's law and Ampere's law, but you will see that Maxwell has made a very important contribution here and combined these 4 equations to describe the electromagnetic phenomena of light, and that is why this set of 4 equations bear his name, right. So, in general, what we have seen, the 6 scalar functions of position and time are required to describe the electromagnetic field in a medium. So, fortunately, these 6 functions are interrelated. So, the electric and the magnetic field, why 6? Because E and H both are having the Ex, Ey, Ez, and then Hx, Hy and Hz. Okay. So, they are all interconnected, and they are basically you got to satisfy the set of coupled differential equations, which are nothing but this Maxwell's equation. So, if you see carefully, as I mentioned, that the first equation is derived from Gauss law, that tells you that the electric flux out of any closed surface is basically proportional to the charge density that is enclosed in the surface. The second equation tells you about the Gauss law for magnetism, that tells you that the net magnetic flux out of any closed surface is going to be 0, because you do not have magnetic monopoles. The third equation is basically Faraday's law, which tells you that a changing magnetic field will produce a circulating current. Okay. And the fourth one is called Ampere-Maxwell's law, that tells you that the generation of magnetic field can be done in 2 methods, either through electric current, as well as you can have changing electric field, right. So, here you can see the representation of this bold characters. So, E is for the electric field vector, H is the magnetic field vector, D and B are basically electric and magnetic flux densities respectively. Rho is the charge density, J is the current density, right. So, the Maxwell's equations are basically valid for both static and dynamic electromagnetic fields in a medium. Now, let us carefully look into each of these equations one last time in both integral and differential form. Okay. So, Maxwell's equation can be written in both integral and differential form, we will see that. So, the Gauss law for electric fields tells you that while the area integral of the electric field gives a measure of the net charge that is enclosed, okay, that you can see. So, you have basically taking the area integral of the electric field, okay, that is giving you the net charge, or you can just take the volume integral of the charge density, that is also fine, you are getting the net charge. But when you go for the divergence, it actually gives you the measure of the density of sources. So, the divergence of D gives you rho v. So, that is important to understand that both forms are correct. Maxwell's equation can be written in the integral form as well as in the differential form. The choice between the differential and integral forms depend on the problem statement or the kind of problem you are going to solve and the desired level of details. Okay. So, typically people use differential form, which is useful for calculation in localized regions, while the integral form is helpful for relating fields within a region to those on the boundaries. Okay. So, one can say that use the differential form when you need to understand the local behavior of the fields at a specific point, or when dealing with complex or less symmetric situations, and you can go and use the integral form when you want to relate the fields within a region to those on its boundaries, okay, especially when dealing with symmetric distribution of charges and currents. The next one, the Gauss law for magnetism, tells you always that the net flux is going to be always 0 for dipole sources, okay, and this is the integral form and the differential form for the second law. So, del dot B equals 0, and here surface integral of bt ds is 0. Okay. So, if there were a magnetic monopole source, you would have got a non-zero area integral, but as you have got no magnetic monopole possible, so you just get 0, right, in this case. Faraday's law tells you the line integral of the electric field around a closed loop is equal to the negative rate of change of the magnetic flux through the area enclosed by the loop, and that is in the integral form. Same thing also you can see that you can read from here that the time varying magnetic flux gives you a rotating electric field. And the fourth law, Ampere-Maxwell's equation, this gives the total magnetic force around a circuit in terms of the current through the circuit plus the any varying electric field through that particular circuit, which is also called as displacement current. So, the Maxwell's equation in integral form can be written like this: IT is nothing but line integral of ht dl, that is same as minus surface integral of the current. Okay. So, you are basically taking current density and doing a surface integral. So, you are getting the current plus the change in the displacement field. So, that is basically the displacement current. So, in the differential form it looks bit tidy. So, you can say curl of H equals Jt plus dot d dot t. So, this is basically the displacement current component. Thank you. So, this is all for this lecture. So, we will go into bit more details of Maxwell's equation and wave equation in the next lecture. So, if you have got any doubt and query regarding this lecture, you can drop an email to this particular email address mentioning the lecture number and the course title. Thank you.